All right, good evening, everybody. Let's send Black Hat 2016 out with style. You're in Lagoon K, and you are going to be seeing an AI approach to malware similarity analysis, mapping the malware genome with a deep neural network with Konstantin Berlin. Without further ado, your speaker.
Okay. So thank you for staying here for the last session and not leaving. But today I want to talk about malware similarity. And the reason why I want to talk about malware similarity is because malware similarity is fundamental to pretty much any kind of analysis you want to do on malware. So if you want to detect malware, that's basically malware similarity. You want to do attribution. You want to say who hacked the DNC. Well, it's again about malware similarity. You want to do, you want to have a triage system where you want to reverse malware. Again, the fundamental basis of that is going to be malware similarity. Now, the second part is AI. And so we have malware similarity, but why artificial intelligence? And the reason why you have artificial intelligence is simply the volume of data that you're currently experiencing. So I probably don't need to tell you guys that the number of attacks on an enterprise network has been basically increasing exponentially. And given the amount of data that we have, to understand what's going on, right? So you're defending this enterprise network, and you need to understand what's going on. And the only way you can make sense if you have some sort of augmentation, which can process the data and figure out what's important and figure out some sort of connections, which then they can display, for example, for a human for review. Now, one of the best ways to get this intelligence is through similarity. So let me give you a basic example. So imagine you have an enterprise network. And this enterprise network is constantly being attacked. So you have this malware sample. I don't know if you can see the colors, but you have this blue sample. So you have malware blue attacking, you have malware green attacking, you have malware red attacking. And so the question you might ask, is there any pattern to these attacks? You know, is any of this malware related, right? So if you can identify, if you can say, well, you know, this malware sample, oh, that's related to that malware sample, and I know that malware sample came from this particular, threat actor, then, this one is similar to it, so it probably also came from there. So you can start to get some sort of understanding about what's going on to your network. You can identify campaigns against you, for example, right? You can speed up reverse engineering. You have this huge database of files you already reverse engineered. You find this new previously unseen sample. You find the most similar sample in your database that you already reversed, and then that speeds up your process potentially, right? And lastly, it helps you with mitigation, right? If you have samples that are related to each other and they're being done by the same threat actor, maybe it makes sense to make a Yara signature, or maybe it makes sense to modify some network rule in order to prevent, C2 communication. So what you have to do is you have this huge database of malware, and your task is to find a similar one. That's basically the fundamental task. It's how's it done? And it's done basically, and there are two fundamental steps to that. The first step is you have this malware file, and you extract some sort of set of attributes from it. And they could be any set of attributes. So if you go to the vendors downstairs, everyone has their secret sauce that they extract from this file, right? Some extract byte engrams, some decompile the file, extract opcode engrams. Some even run this file in a sandbox and extract dynamical information. All of that can be expressed as sort of this list of features. Which I have here. So this ABCDE symbolizing some set of features that you extract from the file. So you take this set of features, and what you do is you embed it into a map. So if it's a two-dimensional vector, you can plot that on a two-dimensional map. And so you plot it on a map, and you get this new sample that you haven't seen before. So first you plot all the previous samples that you have seen. And then you plot this previously unknown sample, and you see, which are the closest samples to this, right? So that's basically all it is, right? Once you do that, then you sort of have your potential samples, and then you can proceed to do whatever you want, right? But that's sort of the fundamental task that you need to do before you can do anything else. And there's been lots of research into this, and millions of dollars poured into this. And so when you buy some sort of a triage system, when you buy some sort of intelligence systems, a lot of the money that you spend for this kind of research. You spend for the secret sauce that they have for attribute extraction, and you pay for the secret sauce in how do you find, you have a billion samples, how do you quickly find the most similar sample in this high dimensional space? Okay? But, you know, like with anything else, there is an issue with this system. And the issue is there is more than one way to make a map. You can extract lots of different features, and you can give different importance to each feature. And you can combine the features together. But what is the right way to combine these features to create the right map? So let's start with a pretty simple example, right? You go to vendor number 1. You know, they use their secret sauce, and they extract some set of attributes. Let's call it AB. And then they map a bunch of malware, and then you give them an unknown malware, and they look at the map and they say, well, you know, this unknown malware, it's green, right? It's green malware. Now, you go to a different vendor, and they happen to have extracted a different set of attributes, and they weigh them a little bit differently. And, you know, according to their secret sauce, it's not green, it's blue, right? So if you're doing attribution, for example, right, this could be a very huge mistake. You know, did the Russians hack DNC? Was it someone else? You know, these kind of mistakes can cost a lot of money and can cause a lot of heartache. So the fundamental problem here is how do we get consistent results? So you have a specific set of problems. You want to classify actors, threat actors, right? You have your own list of actors. This vendor developed this secret sauce for extracting features. How do you make it consistent? So if you buy a feature set from the first vendor, or you buy a feature set from a second vendor, that in the end they will sort of give you the same result if it's possible to extract that kind of information, right? So the question that I want to sort of address today is, given a set of attributes, let's not directly map these attributes directly onto this map and try to find similarity. Let's figure out how do we take that and how do we make the best map that we can possibly make given those features. How do we remap everything in an automatic way such that there is no longer, it's not about luck, you get consistent results no matter what features that you're using, right? So consistency is critical here. And I guess before I explain my approach, I want to talk about what is it ideally? What do you have ideally? What is a perfect world, right? A simple world that we can, what's a simple world that we can have in which, you know, if we had that world, then our problems would be solved and we don't need to do anything because we can directly measure distances in that world. So what I would like to do is imagine this world of malware factories, right? And each malware factory produces sort of very similar malware. And if you put them on a map, they sort of cluster together next to each other. And these malware factories, right, they're on the map, and the distances between those factories make sense. So if factory 1, you know, uses secret sauce that's similar to factory 2 that uses also almost the same secret sauce, right? Maybe they're two different threat actors from China, right? But they share a lot of the secret sauce between the two, right? They would be close on the map, but you know, threat actors that don't share anything together, they would be far away on the map. And so you want this map, right? This is sort of an ideal environment because these little malware samples, they all cluster next to each other, and the factories and the distances make sense. And the dimensions might not make sense, but the dimensions use only the vital information. So for example, if there is, you know, you extract a bunch of features, let's say extract some sort of printable strings from a file, right? And it might be that pretty much every file, you know, has this one string in it. I don't know, let's say print, right? So print is not a useful feature for figuring out attribution, for figuring out anything, right? But you don't know that ahead of time, so you extracted it. What you want is you want a system that says, once you remap this original set of attributes, this feature, this print statement, it's no longer going to be represented in the map. So whether there is a print statement or there is no print statement in this particular file, it doesn't affect how this file is mapped onto this sort of idealized world, right? And there is sort of, and if you pause and you think about it, and there is sort of like this one problem with this, right? This is completely made up, right? If this was a reality, we would be done. We don't need to do anything, right? And, well, I mean, so it's imaginary, and if it's an imaginary, it's pretty useless. So why, well, I mean, why even talk about this, right? And then, if we pause and think about this, we realize that not only is that world imaginary, everything, there is no spoon. This whole entire mapping that we had, the inconsistent mapping, all of it is made up. And all of it is made up by us, right? Because we are the ones that made the choice to extract a specific set of attributes from the file. We are the ones that chose to weigh them in a specific way. And because we chose everything, because the whole world is fake, we can change it. We can morph it, just like you can bend a spoon in the matrix, right? And there are lots of ways you can bend the spoon, or you can bend this sort of map. But one of the best ways I know how to do it is using deep neural networks. And what this deep neural network, the idea is going to be that we're going to take this original set of features, and we're going to somehow pass it through this deep neural network. I'm not going to tell you right now how we actually learn this deep neural network, but it does this complicated morphing. Imagine a two-dimensional map of the world, you know. The distances between cities don't make too much sense depending on where you are on latitude and longitude. Well, latitude, I guess. But after we do this thing, right, it becomes this globe where everything actually makes sense, where the distances actually are consistent. And so that's sort of the hope. This is what we want to achieve. It's great, but how do we do that? It seems like a very daunting problem. And this is where deep learning, artificial intelligence, machine learning can come and help. And the idea here is going to be, we're going to use what's known as a variational AutoEncoder. Now, variational AutoEncoder is a very complicated, hard mathematically to understand piece of machinery. But the actual math behind it is probably not important here. What's important is sort of the intuitive idea behind this variational AutoEncoder. Variational AutoEncoder says, we want to remap our original map into this new map in a specific way. And it's going to balance two sort of conflicting ideas. One conflicting idea is that there's only one factory. All malware is the same, produced by the same malware factory, right? And that's okay. That's a very simple world, right? That's the simplest world we can think of. But on the other hand, it also needs to cluster malware families. So once you map this malware into this new map, it has to cluster. And how it clusters, we can define that. Specifically, I'm going to be using family variant, Microsoft family variant names here. So if you have Virut sample, right, it needs to cluster with Virut. But if there's only one factory, it cannot possibly cluster, right? Virut cannot possibly cluster because everything is one big glob. It's all produced from the same factory. And when you do this, when you set these two conflicting goals, right, you cannot satisfy them, but you're going to try to satisfy both at the same time as much as you can. What happens is it actually squeezes this secret sauce out. Like this useless feature, this print statement that you had, that's going to be squeezed out. And what you're going to have is only things that are critical for the system. Because if it's a useless feature, then you can drop it and get closer to only one factory idea. And if it's actually useful, then you can't, if you drop it, you're not going to be as good at clustering as you could have been otherwise, right? So by balancing this system, you can create, you can sort of map this into a world where everything is important, where all the dimensions are important. And so how does a variational AutoEncoder work? Well, it's a fairly complex piece of machinery, so I'm just going to sketch it out a little bit here. And so the idea is the morphing. So the morphing is a fundamental thing, right? We're going to take our original set of features, and we're gonna embed them. We're gonna transform them into this new world, this new map where distances make sense. And once we transform them, we're gonna do this thing where we're gonna try to map them back. We're gonna try to map them into their families, right? So we transform it into this new space, and then we take this point in this new space and we transform it into a family name, right? So if there's good separation, then this transformation works. But if they're all clubbered together, then this transformation is not going to work. And to make things harder, right? Because we don't want this system to be. We don't want the neural network. We don't want it to be too easy for the neural network to do this, because we want a robust system. What we're going to do is, before we transform it into a family name, we're going to add a bunch of noise to it. So again, to sketch it out, what do you have? You have your original feature set. It's morphed into this new better map, right? This point in a better map. You take that point, you add some noise to it, and then you make it, and then you map it into a family name that it belongs to, right? So you need labels for this. This is a supervised approach. And because it's a supervised approach, that's what's going to make things better, right? Because just arbitrarily extracting features and hoping things cluster together, that's an unsupervised approach. And whenever you add labeled data, you typically tend to perform much better. And so you take this whole system, you take your family labels that you got, let's say, from VirusTotal, and you learn. You start learning. You start using backpropagation, direct backpropagation neural network, to actually learn. You learn. What do you learn? You learn this the encoder, this morphing, this neural network that's responsible for the morphing, and you learn this decoder. So you learn both things at the same time. And I think it helps to actually, because this is fairly complicated and hard to understand. There is a lot of math involved, a lot of transformations. I think it helps to actually visualize a simple problem. And as a simple problem, what I did is I picked a simple system. I picked 8 family variants. So you see them on your left, no, on your right. So you see it on your right. So there are a bunch of different malware. Notice specifically there are 3 variants of the root in this example. So there are 8 total variants, and most of them are coming from different families, but 3 of them are coming from the root family, right? And we are going to embed. Now, typically, you can embed in a high-dimensional system you develop into 1,000 dimensions, right? The higher the dimensions, the better the results, probably. But we're going to use a 2-dimensional embedding. So we're going to transform the original feature set, whatever it is, and in this specific case, it's actually 1,024 features. And we're going to squeeze them down into this new map, which is only going to have 2 features. So this new vector that you will get, this new map is 2-dimensional, and each point has 2 features in it. Secret sauce A and secret sauce B. Okay? And we can play around, right? So we can say, well, what happens if you only care about the first part of the variational AutoEncoder? What if you only care about, what if everything is one factory, right? And the alternative is, forget that, forget this one factory rule. Why don't we just concern ourselves with clustering, right? Basically, that the whole family must cluster together, families must cluster together. Well, if you say everything is one family, everything is one factory, right? Then, well, everything collapses into singularity. There is only one factory. There is nothing here. So all the samples are on top of each other, and you learn nothing, you understand nothing. On the other hand, if you say, sorry about that. On the other hand, if you say, I don't care about this one factory rule, I don't care. I only care that we cluster. Well, then you do cluster, and you cluster fairly well. But what happens is your neural network, it tries to separate the malware too aggressively. And so the distances between families, they stop making sense. It becomes this sort of isolated system where you have one sample here, and then long far away you have a different sample and another sample. And so, for example, the distances between the root samples, they don't make much sense. There's large distances between them necessarily. The distances inside the family, inside the cluster maybe makes sense, but the distances between clusters, they're no longer active here. But if you pick this sort of Goldilocks happy medium between the two, it's sort of a compromise, right? At the same time, it tries to be this one-point singularity, but at the same time, it has to fit the family names. And so it's this mix, and the distances start making a lot of sense at that point. And so that's sort of this toy example, but we actually evaluated the system much larger on actual examples. And so we took 800,000 samples from VirusTotal. These samples include 1,500 family names. So 1,500 family variant names from Microsoft. That's pretty much every family variant that Microsoft has that's currently active in the wild. Provides 99% coverage. So that's a lot of labels. And we're going to do this time split validation. We're going to split this set. We're going to take old samples, and we're going to train this variational autoencoder system. Right? And we're going to run it using we're going to train it using backpropagation, using the labels we got from VirusTotal, for hundreds of epochs until we reach a pretty good solution. And then we'll take that, if you go back here, we'll take this first part, this encoder, right? And we're going to remap that. We're going to use it to remap the original sample. So we extract some sort of features from it, and we're going to remap those features using the first component, the encoder part. And we're going to put it on a map, and then we're going to measure how well we do. And the way we're going to measure how well we do is using this 3 nearest neighbors classifier. So what do I mean by that? I mean, let's take the training data. So this is some old data, and we're going to run it through this encoder, and we're going to put it on a map. So now we have this huge database of points, let's say 400,000 points, with different labels on it. Now we take a previously unseen sample, we run it through this encoder, we put it on the map, and then we say, okay, what are the 3 closest samples to this unknown sample? And let's say 2 out of the 3 are Virut. Then we say, this new sample must be Virut. And then we go and when we look at the actual label that we had hidden, and if we are correct, we give ourselves a point, and if we're incorrect, we subtract a point. And if you do that, it aggregates into this statistic called the F1 score, which is basically precision and recall combined together. And that's how we're going to evaluate. Are we getting better F1 scores? And there's going to be a second way to evaluate it. So we're going to look at 2 features. So imagine vendor 1. He's not a good vendor. His features are, I'm going to extract printable strings from the sample, and I'm just going to use that. And I'm going to min hash them for whatever that means. It's not important. And we're going to have vendor 2, let's say Invincia, who happens to have a deep neural network detector, right? And they have this advanced set of features that is really good at detecting malware. So let's take those features, right? So those are going to be the 2 features we're going to be looking at. And let's see if you can improve them, right? So if we just take the raw data, what we have is a pretty bad triage system. There is an F1 score, but the point here is what I'm plotting in blue. The blue is the distances between points inside a family. So if you have 2 samples that are Virut, you expect that the distances between these 2 samples would be smaller than from Virut to some other malware that's unrelated to Virut, right? So that's what we're plotting. We're plotting a histogram of these distances. So we take 400,000 points and we plot the histogram. And so you would expect a separation, right? You would expect more blue having smaller distances and more orange having bigger distances. But we don't really have that. They're about the same on average. And that's because strings by default are not that great, right? And there's been a lot of research in using strings, and they're actually pretty good. And the reason they're pretty good is because people play around with it. They try to weigh them in the specific magical ways, right? But we're not going to do any of that because we have a better system. We have this neural network that we train. And once we do that, once we remap from the original really bad map into this new map, what you start seeing is even the strings you start having a pretty powerful detector. You start seeing clusters, right? You start seeing samples that are coming from the same family. They have much smaller distances than distances to samples from other families, right? But that's fine. The question is, does this work if you take a really good feature set, right? And so what we did is we took a much better system, right? And if you use the deep learning features, you already have pretty good separation, which makes sense because they're able to identify malware pretty well, right? They're able to classify malware. But if you run this system on them, right, it automatically improved them. So what we are seeing here is a way to take whatever set of features you extract, right? So you have one set of features today. You wake up tomorrow, you think of better features. You add those features. And all you have to do is not hire 50 engineers to try to figure out how to integrate this new set of features with your old set of features. You use supervised training, use variational AutoEncoder to create this secret sauce world, right, that only looks at important things. And so this original problem that we had in the beginning, where if you use printable strings, you get one solution, where you use deep learning features, you might get a different solution, that more or less goes away because we don't care with what feature, well, we do care to some degree, but we don't care as much with what features we start with. We only care about with the features we end with. And because we train them against labels, it brings consistency to the whole system. And so you can be more confident that the results you're getting are actually true results. So you can imagine you have two organizations, right? Imagine you have Kaspersky and you have Microsoft or Symantec. Kaspersky has one set of families, right? And they care about identifying that. They define families in a certain way. But Microsoft has a competing definition of malware families, right? So you have, if you're building a system, right, you design your system, you figured out how to properly weigh the features such that it's pretty good at working on Kaspersky data, and then you transfer that system to an organization which is more interested in Microsoft family names, it's not going to work as well because you didn't tune it for that, right? But if you do that, but if you take the features and we use the system to remap the data, right, it automatically tunes it. And because you can tune it, right, it's very easy to adjust to different problems, right? We don't have to use labels from Microsoft. It could be anything. It could be, NSA might have their secret labels we don't know about, right? You create the system, you hand it off to NSA, and they retrain their system, and it works, right? You don't need to know the internal details of what the clients have. All you need to do is provide them a way for optimizing their system so it works optimally as well as it could possibly do. So there are several takeaways from this. And the first one is that developing features is expensive. Developing the similarity system is expensive. But you don't want to start from scratch. You want to develop something that can take the already existing systems and just slightly modify them, right? Because that's the cheapest way of going about it, such that it works to the best of its ability, right? The traditional systems are hard to tune, as I explained, because you're sort of manually trying to figure out how to combine these features together. But by leveraging labels that approximate the semantic task, sort of the general idea of what you want to accomplish. If you can get labels that approximate that task, you can actually get a significantly better result. You can get a significantly better similarity search system. And because you have this system, you can retrain it. And retraining costs you nothing. Once you get new samples, new labels, you rerun your neural network, right? And so malware evolves, families evolve, everything evolves. You don't want to pay people every time, every month a new type of malware comes out. You don't want to pay a team of engineers to re-engineer your features. It's expensive and it's not optimal, right? And because now, you can move from a system that you buy and then maybe 2 years later you update. You move to a system where you update every day. You move to a system where an update costs you nothing, and you have this completely different paradigm for this fundamental thing that provides vital intelligence to an enterprise right, for an organization. And I guess with that, I would like to conclude and thank my coworkers for giving me some valuable feedback, Invince Inc. for enabling this kind of research. And there is more information, and just so everyone knows, we are actively hiring. So if anyone here interested in machine learning, intersection of machine learning and cybersecurity, we have some exciting projects you can work on.